Today I'm going to be going over Kirchoffs Voltage and Current laws. These are very important laws that you're definitely going to want to have a good understanding of to do further circuit analysis. Before I start talking about the actual voltage and current laws, I wanted to establish a basis. There's two things you really need to understand. The first is how current interacts with circuit elements and how voltage interacts with circuit elements. I'm going to just use resistors in these examples to keep things simple, but in most cases these can be applied to other elements. Current, I, is the same. These resistors are in series. Current is the same in all of these elements. So I is the same here and here and here. It's the same current through all three of these resistors. However, voltage, I can draw it, is different. Voltage in series. This is a different voltage, V1, then V2, then V3. And as we explained earlier, these voltages are defined by Ohm's law, which is dependent on the values for these resistances. So the voltages are different at all three of these resistors, but the currents are the same. That's for series. Now, in parallel, say we have R1 and R2, and R3 just for consistency. The current is different in each one of these branches. So these are all different currents in each of these resistors. However, the voltage is the same across all these resistors. So voltage here is the same as here, is the same as here. And you can find the currents using Ohm's law once again, as we did in the first video. So now that we have this basic understanding, I'm going to use it in our application of Kirchoffs Voltage Law, often called KVL. So we'll start with an example. While I'm drawing this, I'll explain the basic principle behind this. It's based on conservation of energy, meaning that the total voltage of the system when added together should equal 0, because you can't create energy. You can't just create it out of anywhere. So whenever we analyze this and find all the voltages, it should add up to 0. And what we want to do is basically find the voltages here, here, and here at all these resistors. So we can find the equivalent resistance of V1 of R1, R2, and R3 to find the current, because we know how to do Ohm's law for a simple voltage source and a single resistor. So these are in series, so we're just going to add them up to find the equivalent resistance, where this resistor equivalent is equal to R1 plus R2 plus R3, which equals 7.5 plus 10 plus 5 kiloohms. They're all in kiloohms. So that works out to be 22.5 kiloohms is our equivalent. So now that we know the resistance, we know the voltage, we can find the current from V equals IR. 45 volts equals current times 22.5 kiloohms. Keep the units, they're important. And that works out to 2 milliamps. Okay, so we know the current, and we know that this current is what runs through each of these resistors. So we know the current here, we know the current here, we know the current here. We also know the resistance at each one of these resistors. So with that knowledge, we can apply Ohm's law at each of these resistors. Make sure I got this right. Okay, so start with R1. For R1, the voltage would be, say V equals IR. What do we want to find here? Voltage. So we take the current of 2 milliamps, multiply it by 7.5 kiloohms, and this is just the voltage at R1. Since it's in series, we're going to add same current, 2 milliamps, there's 10 kiloohms, and then this is just voltage at R2, and then move down here times 5 kiloohms. This is just the voltage at R3. So let me go ahead and move this down here so we have a little more room. Okay. So if you work the answer for each of these, you will find 45 equals 15. 20, 10. These are all in volts. Make sure you keep the units, usually they work out to be pretty nice, but this is definitely something to watch out for and bear in mind. So as you can see, it's a true statement. It adds up to be 45 volts equals 45 volts. Now all that shows you is that the voltages from here over are the same as the source, which means there's no other voltage source. So basic principle applied by the voltage law, and a fairly simple example. Current law is quite similar in that you have, let's say, a junction in your circuit that splits off like it's in parallel. Let's say a circuit like this. And let's say we know voltage, let's call it 5 volts, and R2, let's call it 6 ohms, make these smaller than 10 ohms. And we want to find current here and the current here. It's kind of the inverse of the voltage law. Each of these currents are different because they're in parallel, as we said before. But we know this voltage at this node is going to be the same for both of these resistors. If this is a single node, right up here, and is connected directly to the 5 volt source, we know this is going to be 5 volts also. Which means across both of these resistors, there's a 5 volt drop. So with that knowledge, it's fairly easy to apply Ohm's law. Let's start with R1. For Ohm's law, we know the voltage. We want to find the current, and we know the resistance is 10 ohms. So current is 0.5 amps. Similarly, in R2, we know the voltage is also 5 volts. We want to find I, and we know the resistance is 6 ohms. A little bit messier number, but 5/6 amps. So, the question is, what is this current? I source. What is the current coming out of the source that's going into this block? Well, we know I1 and I2. So to find IS, we just add them together, because the current can only go two places. Here's coming from the source, here's to one resistor, here's to the second resistor. This is your source voltage. It can only go down this path or down this path. This is your first path, this is your second path, and both of these coming out of this junction, let me draw it in red, this junction here, where both of these resistors are connected to, essentially states inputs equals outputs. So whatever's coming in also has to end up going out, which is another conservation application. So in this case, we know we found both of these coming out of the junction here through Ohm's law, and we want to find what the source is. Based on this relationship, IS equals I1 plus I2, we know IS is simply equal to 1/2, or make it the same, 0.5 plus 5/6, which works out to be 1.33 amps. And that is the source current. So what is coming out of the currents, what's coming out of the voltage source. So you can apply these throughout circuit analysis depending on voltages. It can be in the middle of a circuit anywhere, and there's definitely more complex examples, but this should give you a pretty firm basis and some kind of understanding of these laws.